Guglielmo Marconi was born in Bologna, Italy in 1874. He showed an interest in science at an early age, the idea of communication via electromagnetic waves in particular. As a young man, he studied the work of James Clerk Maxwell and Heinrich Rudolf Hertz, who did groundbreaking work in electromagnetic theory. Marconi experimented with transmitting electromagnetic waves in his parents' house, succeeding in doing so over short distances. By 1894, he was conducting experiments in a laboratory setting where he gradually discovered how to increase the distance of transmission. However, he had yet to prove that electromagnetic waves could travel over thousands of miles. Electromagnetic waves enable wireless communication. These waves can travel in free space, as demonstrated by a fluorescent tube glowing in the presence of an electromagnetic field produced by a radio transmitter. Nikola Tesla theorized that electricity could be sent this way, eliminating the need for wires. He attempted to prove his theories and used some of the principles that Marconi used. The wavelength of an electromagnetic wave depends on its frequency, the number of cycles per second expressed in hertz, named after Heinrich Rudolf Hertz, who discovered the frequency characteristics of these waves. EM waves exist in nature at various frequencies and wavelengths. Frequency is defined as the period between the peaks of successive cycles of a wave. The higher the frequency, the closer together the wave peaks are in time. Wavelength is the actual distance between waves at a given frequency. The higher the frequency, the shorter the wavelength. The speed of light is a constant that applies equally to all EM waves. The frequency of a wave multiplied by its wavelength will always equal the speed of light. Wavelength determines where the EM wave falls on the electromagnetic spectrum, expressed in meters or fractions of meters. Since electromagnetic radiation travels at the speed of light, in mathematical terms, the speed of light divided by the frequency of the wave equals the wavelength. For example, the wavelength at a frequency of 1 million hertz or 1 megahertz is equal to 300 million meters per second divided by 1 million or 300 meters. Frequency and wavelength are separate phenomena, but related in that frequency determines the wavelength, and therefore the form of the wave and its suitability for a particular purpose, such as radio communication, lighting, or heating food in a microwave oven. Wavelength also affects the propagation characteristics of the wave, how it behaves in free space. Depending on their wavelength, electromagnetic waves can be visible or invisible to the human eye. James Clerk Maxwell theorized correctly that light is an electromagnetic wave. Visible light appears on the electromagnetic spectrum between microwaves and X-rays, transitioning from infrared light, which is invisible to the human eye, to visible light, and then to ultraviolet light. As the frequencies of the waves become higher, the wavelengths become shorter. While visible light is considered a wave, Albert Einstein proposed that light is comprised of energy packets called photons, meaning that light also behaves as a particle. Electromagnetic waves can be absorbed, diffused or spread out, or refracted, that is, bent, by materials on Earth. The degree to which each of these occurs depends on the atomic structure of the material. For instance, light can pass through glass because glass atoms do not absorb light waves. Radio waves, at the lower end of the electromagnetic spectrum, are easily absorbed by water and therefore are reduced by rain. Electromagnetic waves also travel at different speeds through different materials depending on the atomic structure of the material and the frequency of the wave. Materials that absorb light and then emit it later in a delayed fashion change the speed at which the light is traveling, which can refract or diffuse the wave. Light shining through water illustrates this phenomenon when viewed from below the surface. The prevailing belief among physicists in Marconi's time was that wireless communication over long distances was not possible due to the curvature of the Earth. Marconi's peers thought that electromagnetic waves would travel in a straight line to the horizon and disappear into space as the Earth fell away. In opposition to that belief, Marconi theorized that the distance signals traveled would not be inhibited by the Earth's curve because they would follow that curve. His theory proved to be only partly true. Marconi's theory that radio signals could be sent over large distances unimpeded by the curvature of the Earth was correct, but for a different reason. While the signals do travel in a straight line to the horizon, the ionosphere surrounding the Earth refracts the waves, causing them to bounce or skip, traveling the great distances that Marconi had imagined. The degree of refraction is dependent on the frequency and wavelength. The electrical telegraph, invented by Samuel Morse in 1837, was the first long-distance electronic communication system. Using Morse code, a series of electrical pulses representing letters of the alphabet, messages were sent and received over wires to distant places. However, the fact that wires were required limited the reach of electrical telegraphy. Marconi believed that he could send telegraph signals anywhere on Earth using radio waves, eliminating the need for wires. He was eventually able to prove his theory by transmitting the first wireless telegraphy signal from Cornwall, England to Newfoundland, Canada on December 12, 1901. In so doing, he proved that long-distance communication via radio waves is possible. Many today view Guglielmo Marconi as the inventor of radio. That belief is only partly true. Some clarification is in order. Like many great scientists throughout history, Marconi built upon the work of others. He applied the theories of past physicists who had studied electromagnetic waves and created the means by which wireless communication over long distances was possible. His efforts created the foundation on which wireless communication as we know it today was built. Early physicists, such as Maxwell and Hertz, did not see the practical implications of electromagnetic waves in their time. Scientists and inventors that followed continued to seek ways to make practical use of electromagnetic radiation, particularly for communication. Inventors such as Sir Oliver Lodge, Edward Bromley, and J.C. Bose developed devices to send and receive radio signals as early as 1894. At that time, Nikola Tesla was also researching uses for electromagnetic waves. However, he focused most of his efforts on developing the technology to transmit alternating current wirelessly on a global scale. With various individuals working to find uses for electromagnetic waves during Marconi's time, controversy developed around who should take credit for inventing radio. Patent disputes for radio inventions continued in the courts for many years across international borders. In 1943, some of Marconi's patents were awarded posthumously to Nikola Tesla. Historical evidence seems to suggest that the technology that enables radio communication was not invented by one person working alone, but by many, building on each other's discoveries and inventions. It was Marconi, though, who brought all of these innovations together, demonstrating a practical use for the technology. Marconi also became the face of radio and its champion, gaining support from influential individuals and the public. Without that support, radio may not have grown to become the accepted technology that it is today. Learning how to harness the power of electromagnetic waves has enabled the communications medium now called radio. However, the practical application of that knowledge has also enabled other technologies that benefit society. Cellular phones are now common almost everywhere and owe their existence to the study of electromagnetic theory and the development of radio. Radio frequency energy is also used in MRI scanners to create highly detailed images of the human body for diagnostic purposes. High-frequency radio waves heat the food we cook in our microwave oven. Wi-Fi enables the connection of computers on a network without the need for cables. Satellites, sending information to any point on Earth, would not be possible without the inventions and vision of physicists like Marconi. Radio communication is Marconi's great legacy. The work of Guglielmo Marconi resonates with me because I've been working in the industry that he made possible. Working as a radio engineer for the last 30 years, I work with the principles that Marconi used to deliver the first long-distance radio transmission every day. I work with devices that are descendants of Marconi's inventions. Radio transmitters, antennas, and receivers make up the delivery system of the radio broadcast medium. Entire industries, including mine, have been built on the work of Marconi. A radio experimenter as early as age 8, I later became a ham radio operator and received my first commercial broadcast radio license from the Federal Communications Commission at the age of 15. Amateur radio and citizens band, or CB, were social media back in the 70s, many years before the public internet. I was the go-to guy for radio advice among my friends in high school. Like the early physicists, I studied electromagnetic fields and built electromagnets by winding wire around an iron nail, connecting it to a battery. Then, I built a working electric motor from plans I found in a book. My interest in electromagnetic fields eventually led to my involvement in radio, following the path of those who had studied and innovated with electromagnetic fields in the past, such as James Clerk Maxwell, Heinrich Rudolf Hertz, and Guglielmo Marconi. As a teenager, I took my interest in radio to the next level, building a working broadcast radio station in my parents' basement. I built the audio console out of spare parts. The transmitter was a modified ham transmitter that I bought at a consignment shop, and I put up a pole in the backyard with a homemade antenna. My broadcast, such as it was, could be heard in our neighborhood from midnight until 4 in the morning. Needless to say, I got little sleep. My signal didn't go very far, or violate FCC rules, but it was a thrill for me to think that I was on the air, even if no one was listening. When selecting a physicist that had an impact on my life, the choice was clear. Marconi's work created the interest in me that has endured for over 50 years. My hobby advanced to formal education in electronics, and ultimately to a career working with the principles that had fascinated me early in life. The theories and inventions of Guglielmo Marconi inspired me to pursue a career in radio and electronics. Radio impacts my life on a daily basis because I work in the industry that Marconi helped to create. Radio and the field of electronics might not exist today without the past knowledge gained through the efforts of many great physicists. It was Marconi who took that knowledge and devised uses for it that impacts the lives of many people worldwide every day.